Hello, my name is Nikhil Kumar, and welcome to my Lab 6 Magnetic Molasses Physics 2212. Okay, so in this lab, we explored Faraday's law by dropping a bar magnet through a tube of aluminum foil and observing how the induced current slowed the magnet's fall. And then we built a computational model in GlowScript to simulate and compare results. So we found that so preview our final result is that we found out the time it took for the magnet to drop increased when we dropped it in the tube, and that the magnetic field slowed the dropping of the magnet. The average time it took to drop the magnet was 1.834 seconds, and the computed time using GlowScript was 1.668 seconds. Okay, so here are the main concepts of the lab. Biot-Savart's law, Faraday's law, and Ohm's law. The Biot-Savart law tells us that moving charges produce magnetic fields. As the magnet fell, it produced a changing magnetic flux through each ring of the foil tube, and by Faraday's law, that changing flux induced an EMF in each ring. Finally, Ohm's law tells us that the EMF drives a current based on the resistance of the ring, and it's that induced current interacting back with the magnet that creates the slowing force. And these are equations that show our laws. Okay, so our experimental procedure. Well, first we identified the north pole of our bar magnet using a magnetometer app, and then we held the aluminum foil tube vertically and recorded on video as we dropped the magnet through it. By scrubbing the footage, we've identified the exact timestamps when the magnet entered and exited the tube, giving us the travel time, and then we repeated this drop 5 times to get a reliable average. So our system was our bar magnet, and our surroundings were the rolls of aluminum foil, the earth, and everything else. And then here's a picture of us doing the experiment. We dropped it 5 times, reaching an average time of 1.834 seconds, and we found that the magnetic field was increasing the time it took for our magnet to drop. Okay, so here's a computational model. We used GlowScript to code it, and the bar magnet was treated as a magnetic point dipole, and the tube was modeled as a stack of non-interacting conductive rings. So here's a quick walkthrough of our key steps. So first we set our initial conditions, which you can see on kind of everywhere here. This is basically our geometry of our tube, and then the velocity and start time. And then we computed the dipole magnetic field at each location in the thing, at each part of the ring, and that's on the left. Using Faraday's law, we calculated the rate of change in magnetic flux in each ring, and then applied Ohm's law to get the induced current, which is seen on the left. And then using the Biot-Savart's law and Newton's third law, we calculated the upward magnetic force on the magnet from all the rings combined. And then at the right picture, you see adding gravity, we applied Newton's second law to update the magnet's position and velocity at each time step, and our simulation produced a fall time of 1.668 seconds. Okay, so now let's interpret this. Well, okay, so the first question is the intensity of the coloring on the tube indicates the magnet's magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions, and then they said which direction is which. So if we apply Lenz's law, we show that the induced current must oppose the change in magnetic flux, which requires a counterclockwise current to produce an upward field. And this means that red corresponds to a counterclockwise current, and blue corresponds to a clockwise current. And then what happens to a dynamics of a system when you flip the magnet around? Well, it reverses the direction of the induced currents. However, the overall motion remains the same because magnetic force opposes the magnet's fall. Okay, so and then how does the total time in your tube of your real-world system compare to that of a computational system? And how might the computational system be made more accurate? Well, this is comparing our two systems. The computational model differs from the real system because it neglects air resistance and uses an idealized magnetic field, which our real system should not. How does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The graph shows the forces as balanced for 0.1 seconds and then balanced from 0.1 to 1.4 seconds as seen on the bottom right. Okay, so our assumptions in our experiment is that there's negligible air resistance and that the induced magnetic field is the only magnetic field affecting the magnet's motion. And then our errors is that there could be other magnetic fields present, and we used phone video to record, which could be less precise as it doesn't have the precise time markings. Okay, so our discussion questions are: what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, if it was close to zero, then the resistance would be very small, indicating a large current, and this increases the magnetic force, which increases the time it takes for the magnet to fall. What if there were holes cut into the tube, and how would this affect your ring's current in the model? Well, holes would disrupt the induced current and reduce the magnetic force on the magnet, making it fall quickly through the tube. All right, thank you for your time.